You may have heard about simple machines before, probably in middle school briefly. So we're going to revisit them again and look a little bit at the equations that describe them. We're not going to cover all of them, we're only going to look at three. So today we're just going to define simple machines, mechanical advantage, and the different variables we need, and look at the first simple machine, inclined plane. We'll start with the definition of a simple machine, and it's just a device that changes the magnitude or direction of a force. Mechanical advantage, symbol for that would be capital M, capital A, is the measurement of that change in force. There are four variables we need to look at. The first is input force, and that's the amount of force you're exerting on the object. So that's how much effort you're putting into the machine, essentially, you as the user. The symbol for input force is a capital F with a subscript I-N for input. Output force, we're going to keep it simple. It's just the weight of the object or the load on the machine. So you can think of it as the resistance by the object, and we're going to call that F out, O-U-T. The input distance is the distance over which you exert the input force. That would be D in. And the output distance is the distance the object is moved. That would be D out. This will be different for the three different machines that we're looking at, but we're going to start with inclines. And I'll show you exactly where F in, F out, D in, and D out apply for that. Ideal mechanical advantage is the mechanical advantage when there's no efficiency lost in the machine. It is literally the ideal mechanical advantage. And it's going to be the ratio between distances. So all of these equations that we're dealing with are very simple because they're ratios. We don't have to really deal with algebra, adding, subtracting. It's all dividing. So the equation for ideal mechanical advantage would be IMA equals the input distance over the output distance. And because this is a ratio, ratios do not have units. So IMA is unitless, just like mu. The actual mechanical advantage is the mechanical advantage when efficiency is lost. So this is more what it actually is versus what you would think it would be with a machine, and that's the ratio between the forces on the object. So actual mechanical advantage is AMA, and that's going to equal the output force over the input force. Once again, because this is a ratio, the units will cancel, and this is unitless. And then the last thing we want to look at for machines would be the percent efficiency. Once again, it's a ratio, and that's just the ratio between the AMA and IMA, or the ratio between input and output work. So there's two equations you can use for this. Percent efficiency equals AMA over IMA times 100%, or percent efficiency equals output work over input work. If you recall, work, hopefully you do recall this, equals FD cosine phi. However, the force and the distance are always going to be pretty much in the same direction. So cosine of phi will always equal 1. Therefore, we don't need to worry about the cosine phi. And we're just looking at work equals FD. So your output work will just equal your output force times your output distance, and your input work would equal the input force times the input distance. So when we say percent efficiency here, work out over work in, you could just take this over this, which is essentially what you're already doing when you take the AMA over the IMA. So we're going to look at the first simple machine. That's an inclined plane. We've seen inclined planes before. It's just a slanted surface that an object can be pushed or pulled up. The ideal mechanical advantage on inclined planes will always be greater than 1. And just to explain why, let me label this inclined plane, make it a little bit bigger. So your input distance is going to be here. It's going to be the length that the object is pulled. So that's your input distance. Your output distance is going to be this, the height of the plane. So if you know your triangles, the input distance is the hypotenuse, the output distance is the height. IMA equals D in over D out. Because D in is the hypotenuse, it will always be greater than D out. So therefore, a greater number divided by a smaller number will always be greater than 1. Let's look at an example real quick with inclined planes. We have a 10 kilogram mass pulled by a 60 Newton force 6 meters up an inclined plane that has a height of 2 meters. And we want to know the IMA, AMA, and percent efficiency. So I'm going to start by drawing our little inclined plane. And we have our object, which it tells us is 10 kilograms. And it's being pulled up the plane with a 60 Newton force. It's being pulled a distance of 6 meters. And the height of the plane is 2 meters. So if I list my given information, my input force is 60 newtons because I'm putting in 60 newtons of effort. My input distance is 6 meters since the block is being pulled a distance of 6 meters. My output distance is going to be 2 meters. Another way to think of output distance, if it weren't for the machine, so if it weren't for the inclined plane, and you just wanted to lift the box up, you would start on the ground and you would go directly up. So the distance that the box travels is 2 meters above where it initially was. So the 6 meters is how far it's dragged. The 2 meters is how high you actually want to lift it. Your end goal with an inclined plane is to lift an object from the bottom to the top. So that's why your output distance would be 2 meters, or think of it like the displacement from the original position. It tells us that the mass is 10 kilograms. So output force, F out, is always the weight, which is Fj, which equals mj. So my mass, 10 kilograms, times g, 9.8 newtons per kilogram, equals 98 newtons. So F out equals 98 newtons. And we're looking for 3 things: IMA, AMA, and efficiency. So starting with IMA. IMA equals input distance over output distance. So that's going to be 6 meters over 2 meters. 6 divided by 2 equals 3. Our AMA equals output force over input force. So my output force, which is the weight, 98 newtons, divided by the input force, my effort, 60 newtons. 98 divided by 60 equals 1.63. And then my percent efficiency is just AMA over IMA times 100%. So that's going to equal 3 divided by 1.63 times 100. And this will equal 54.4%. So this particular machine is only about 54.4% efficient, not very high. This is about all there is with inclined planes. You may be asked to find the work done, so the input work and the output work, just to show you what that would look like, because I did give you the equations. And this should be pretty much review. But input work would equal input force times input distance. So 60 newtons times 6 meters, which equals 360 joules. The output force is your output force times your output distance. So 98 newtons times 2 meters, which equals 196 joules. And then percent efficiency, using it this way, equals W out over W in. So 196 joules over 360 joules. And that's going to give us, times 100%, 54.4%. So it doesn't matter how we got there, we still ended up with the same answer, 4% efficiency. Again, nothing terribly complicated, we're just looking at ratios and percentages.